Okay, in the last class, we studied line integrals along a curve. Today's class, we're going to study the so-called fundamental theorem of line integrals. Okay, so this is a line integral, right? And given curve, and this is a curve C. It's oriented, right? And at every point you have a tangent vector, unit tangent vector, right? This is unit, and then you have a vector fields along this curve. It's not necessary to define everywhere else. So this is the F. Then you have this line integral. Okay. Now in case this curve is parameterized by R, right? Okay. Then tangent vector is going to be R prime divided by its norm. So it's unit vector. Okay. So dt ds is going to be this. So when you multiply them out, t ds is just the length is cancelled out. Okay, so this is also simply denoted by dr. Okay, I is a vector. So this is going to be also denoted by dr. Okay, that's called a line curve. Okay, because this TDS can be changed to that in case the curve is parameterized by some vector function. All right. So so what happens? We assume that this vector field is very special. It's coming from the gradient of some function. So you in this domain D, okay, you have a function defined. So this capital F is gradient of some function. Okay, I did not write down x, y, z here. It could be 2 variable, could be 3 variable. Yeah, in case, yeah, it can be 3 variable. Okay, and now if this comes from, if this is a gradient of some function, then what happens? The product, the dot product. Okay, remember, right? This is a gradient of f of dot dr. Okay. So let's simplify it. Let's put the details here. F partial x, f partial y, f partial z. Okay. The dot product here is going to be di is going to be dx over dt, dy over dt, dz over dt, then dt. Okay. Yeah, this is R prime t. Okay. And then you write down the details. You will get right. The bilateral. This is nothing but the derivative of f with respect to t, the composition. Okay, got it? Yeah, when you differentiate, that's what you get, right? It's wonderful. So if we integrate, okay, if you parameterize this curve, you know, t is between alpha and beta, for example, right? Then this line integral TDS, right, is changed to the line integral of, right? It's going to be from alpha to the beta, f r prime dt, right? Yeah, this is just dr. Okay, and then according to our computation, this is going to be the derivative of the function, blah, 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 right? And then dt. Then what? This is the antiderivative. This is derivative of some functions. That's why it is going to be fx beta, y of beta, z of beta, y minus f of x alpha, y alpha, and z alpha. Okay, the difference of the value of the function between the points. Now let me draw the picture for you. So this is a C. Okay, this is a point, the starting point. So it is x alpha, y. Yeah, this is a when t equals alpha, right? And here when t equals beta. When t equals beta, the point is coordinates of point is x of beta, y and beta, and the z and beta at the beta. All right. Now what does that mean? That means it's just the difference of the value of the function at the two endpoints. It's really nothing to do with the path. So in other words, if you have another path going through, as long as it's in the domain, this is a domain D, right? And you have a function f defined, it's a three, here we assume three variables. It doesn't matter. Four variables or just two variables. So you can see that the integral of this line integral, right? Integral itself looks like it depends on C, but this is only the value of the function. Yeah, this is the integral grad f, right? dr. And this is just the value of the function at the two endpoints. Okay. If this is a point P, P0 for example, no, I'm not going to do that. All right. So just the difference of the values of function at two endpoints. Okay. So this is a let me simply write it like this: xt, y over t, z over t, t plus alpha, t plus beta. It's the difference of the various function at two endpoints. So it is independent C. Okay. The exact position of the C doesn't matter. Okay. That's this is a very this is a good approximation. Yeah, this is it's important observation. Yeah. So it's independent of the path from between those 2 points. Okay. So if you have two passes, C1 and C2 have the same starting point and the same end point, and if this is a point I call the P, that point Q, right? Then the integral of C1 F dot T ds, if we use this notation, then it's going to be C2 F T ds. Along different passes, you will end up with the same result. Okay. Now, why this is important? Because if you know the vector field is the gradient of some function, and if I ask you to find the line integral along some path, you can choose another path. You don't need to use the same path to do the computation because it's independent of the path. Okay. For example, yeah, here's a question, right? F, right? X, Y is going to be, that's two-dimensional. Let's use yeah, just use a three-dimensional because I already mentioned three. It is going to be X, Y, Z. About this, right? And here's a path C, X, Y, Z, right? And this is a curve starting from here to here. This is a C. Right? So evaluate this integral C from F to D. Okay. So you look at this example. Well, you can do that directly. Then you have to parameterize this curve, right? You find this is a start from -1 to +1, okay? And the x value is 0. Okay, this is a curve in the YZ plane. Okay. How do you do the problem? Well, you can do it directly, just given the function without checking, right? So then you have to parameterize it. You have to do the counterclock, they have to do the clockwise. Okay, how to do clockwise, right? You can parameterize it over t, right? Then that is going to be, yeah, x is going to be always 0. Y, yeah, usually it's cosine, that's pi minus t, I think, starting from here. When t equals 0, it's pi. When t equals pi, it is going to be 0, yeah. Sine pi minus t, okay, because it's counterclockwise. That's right. It's clockwise, yeah. It's clockwise. Okay, so you can see that when t equals 0, you get 0, -1, and 0. Okay, and when I equals 1 equals pi, you get 0, 1, and 0. Okay. So you have starting endpoint. So how do you solve the problem? Well, you just needed to do the computation, right? It is going to be 0, and by the way, I can also do okay. This is going to be negative cosine t. This is just sine t. I can change it to that, no problem. Okay, so when you differentiate, that will be sine t. It's cosine t. That's a derivative. All right. Hold on. Sine pi. Yeah, when t is 0, it's here, so it's sine, cosine both are positive. And when t is greater than pi over 2, it's here. Sine is x is positive, y is negative. Yeah, that's correct. All right. So now we have to do the calculation, right? C dot from 0 to pi. What is f? It's just x, y, z, right? X is going to be the x component, so it's 0. Y is negative cosine t. This is sine t. Yeah, this is f. X, y, z. Okay. Then the dot product are prime t. So now when you multiply this out, you will see that it's going to be 0, negative cosine t sine t, plus sine t cosine t, and that's dt. So it's actually going to be 0. In this case, you get 0. Right. Yeah. Now you go back to this problem. The vector field is going to be x, just x, y, z, right? This is actually the gradient of some function. What is that function? Half of x squared plus y squared plus z squared. Right? So when you click the gradient, then just get x, get y, get z for each component. All right. So then, according to the above theorem, C f dot dr is just the difference of the value at the two endpoints. Okay. So at the two endpoints, so this is x squared plus y squared plus. So you really don't need to look. The 2 points is the one on the right hand side is going to be 0, 1, no, 1 and 0, and this is going to be like 0, negative 1, 0. But when you plug into here, that does not change the value, so it's going to be 0 anyway. The difference of the value of the function, those two endpoints, one is at this point, and is at that point. Okay, and evaluate here at this point, and this is going to be 0, negative 1, 0. So that's 0. It's much quicker to do. You don't need to parameterize that. You just need to find out the little f. If it's gradient of some function, then all you have to do is just evaluate the function, those two endpoints, and take the difference. Right. But this is the same argument is true for 2 dimensions. Oops. Okay, here's definition of a vector field. When you say a vector field F we get a new battery. Okay, a vector field F is said to be conservative if F is gradient of some function. Okay. So if the vector field can be a gradient of some function, then we say it's conservative. Then And above the theorem says that if the function is conservative, then the line integral is independent of the path. Now, conversely, one can also show that it is conservative if only if the integral line integral is independent passage. So this is the theorem. It's not difficult to prove, but we can also try to find such f if we want. Okay, so f is conservative, and then if and only if, yeah, it's on some, it's on the connected domain D, if and only if f is by definition, this is that means f is going to be the gradient of some function, right? And then if only if the line integral is independent of the path in D. Now we already proved that if it's conservative, then any path in D, right? This line integral depends only on two endpoints. Okay, the converse is just trying to construct such f, and that's easy to prove that. Okay, prove the idea. I just prove from here to here, right? How do you? This is a domain D. You fix a point. Okay, you fix a point. We assume that in dimension 2 or not dimension 3 the same. Okay, so this is a fix. Then this is an arbitrary point, right? Yeah, this is an arbitrary point. Remember, if such f exists, right, then if such little f exists, then this line integral gives you the difference of value of two functions. So of course, such f is not unique, but we can, as a differ by constant. So this is a fixed, okay? And that is the arbitrary point. I want to construct such f. How to construct? So the construction of f is remember, right? This is going to be the difference. Such f is constructed in the following way. It's just as a line integral for f. Yeah. Okay. And the way I see is an arbitrary curve you take. Since it's independent of c, so no matter which c you choose, you don't get different values. Okay. You can set the function. You can set. Yeah. Let me change this later. I can set the value of the function. This I'm going to find out is going to be 0. Then the function at a different an arbitrary point is given by that. So you find the function, right? So you find the function, then you this is this function definitely is the gradient. This f is going to be the gradient of this function. Okay. Okay, so let's find out such function. This can be dimension 2 and could be dimension 3. Okay. In dimension 2, it's a little bit easier. You only have 2 variables, but the whole argument will be similar. Okay, let's look at the following example. Let capital F X, Y, Z to be y square I plus 2xy plus 3z j. Okay. Okay, so this is a vector defining the space. Is it conservative? Okay. If so, find the little f x, y, z. Okay. Of course, you cannot use the line integral to check this conservative because you don't know the specific c, right? But if you know, if you just assume, yeah, let's try this. If you assume this is a conservative, then this is where we construct the c. Okay, so we can try. You can solve it directly. Okay, we assume gradient of f equals f, right? So that means you have the following partial equations. It's y squared, partial differential equation, 2xy e3z, and then you have this. So you have to solve this equation. Okay, so let's do this. The function f has 3 components, right? So if you integrate, this is the first equation, that's the second equation, that's it. So integrating 1 with respect to x, okay? If you integrate 1 with respect to x, you will get, okay, f x y z, then it's integrated with respect to x, so y is a constant. So x times y, and plus a constant c. But that constant c, where it is my phi? Okay. That constant c depends on yz. Let's do that, right? So because we fix the y and z to integrate that equation. So if the function is in this form, definitely sets on first equation. So you do step by step, right? Then you put into the second equation, then plug it into 2 and 3. Let's try this. Right, just into 2, then you differentiate with respect to y, then get 2y, and c and the y, right? Yeah. So this is going to be 2xy plus, what is the function? 3e, 3z, right? So in other words, the c, okay, so that means the partial derivatives c with respect to y is going to be e to the 3z, right? Yeah. Yeah, I just need to actually just needed the second equation first. This is a partial derivative. So you have integrating this equation 4 with respect to y, okay? Because c is a function of yz, so we fix z. So c is going to be y e to the 3z plus K, but that K depends on Z, okay? Yes. So we almost get the function. Right now we put it back to here, so we get F. We get the function F. Yeah, let's write down x, y, z is x, y squared, y e to the 3z plus kz, okay? Then I have to plug into the last equation 3 over here. This, I have to make sure the third equation is satisfied. Okay. If you plug it into the equation 3, the partial derivative of fz, right? F with respect to z is going to be that term is 0, so it'll be 3y e to the 3z, right? Plus k, right? And this is given by e to the e3z. Right. So that means this means going to be 0. Okay. So that means k should be constant. Is a constant, okay, constant. So now we finally get a function of 3 variables. Okay. So you can get a family of, they're all different by constant k, right? So this, we have, so the f is expressed by this gradient, okay? Then the line integral, then the line integral will be independent of the path connecting 2 points. Is there? Yeah, this is but how do we know? How do we check whether this is a conservative? Yeah, is there any other formulas we can check that? Okay, right. So this is a question. So of course we're lucky, you know. What happens if this is not conservative, right? And then I couldn't find the F. I spent so much time, and at the end I couldn't get it. Just waste of time. Why not? I just claim at the very beginning it's not conservative, right? And how do you check that? You cannot use the integral to check. Okay, it says that if it's conservative, if and only if this line integral is independent path for any 2 points, any paths connected 2 points. This is impossible to check that using this theorem, whether the vector field is conservative. Okay, and what we did here is just assume it's conservative. We're lucky, you know, we're told that it's conservative, then we just go ahead and find it. Suppose you couldn't find the F, and you already spent lots of time here, right? And at the end, then you say you cannot find this little f. Then you say it's not conservative. That's okay, but is there any other better way to do that? Yeah, let's take a look at the 2-dimensional case. Okay, f is going to be x, y, right? P, x, y, and q, x, y, right? In this case, just assume that. If f is conservative, right? That means if this is true, right? Then P x y is going to be the partial derivative of this, right? Q x y is partial derivative of the function with respect to y. Then what you can see, I can see that the partial derivative y p with respect to y is going to partial derivative of q with respect to x. They're all equal to the partial derivative of f with respect to x and y. Doesn't matter, that's a switched order. Okay, the reason is we have this identity. Remember, when we differentiate a function twice in different order, we get the same derivative. Okay, so using that, you can get the above identity. Okay, so if you are given P and Q, how to check whether this is conservative? You just need to look at partial derivative P and the partial derivative Q and to see if they're equal, because this is a necessary condition. Now, what I want to say that it's also a sufficient condition. Okay, I did not mention. Yeah, this is a. Yeah, we have the following theorem. We have the following theorem. Let F be P and the Q. Okay, I'm not going to make it. Okay, a vector field on a domain D in R2. Now, this domain D, I have to say a little bit strong condition. D is simply connected, okay? Not only just connected, simply connected. So let me explain. This is a topological terminology. Simply connect. Then F is conservative on D if and only if the partial derivative P with respect to Y equals partial derivative Q with respect to Y. Of course, the vector field, we always assume differential, but we don't want to talk about this. Okay, repeat again. So, but simply connect. What do you mean simply connect? Okay, as connected. I'm not going to prove that thing, okay? Connected domain. A connected domain examples, okay? This is a connected domain, right? Okay. And these two are disconnected domains, right? Yeah, this is a connected, it's a disconnected. Okay. Okay, this D have two regions. That's easy to understand. But simply connected. Okay, simply connect. All right. Okay. This is a connected too, right? Yeah, because you can, any 2 points, you can always find a path. So this is a connected. but you see the difference between this one and the first one, right? So the first one, you see the first one here, nothing empty inside, right? You can shrink it to a point. But this one, there's hole inside. Topologically, that's different. Have you heard about topology, right? Topology. They're topologically at different regions, okay? So they're not, that's not the same shape. Okay, they look different, but essentially, there's the second one is a hole. So this is a, but not, this is a not simply connect. Okay, it's connect, but it's not simply connect. Yeah, just, you can see that as long as there's a hole there inside, it's not simply connect. But it's connect, it's not simply connect. Okay. Okay. So if we have, yeah, so now you can use, just look at P and the Q, find the partial derivatives. If they match, then it's you can find them. You can find yeah, you can find the little f, so that vector field is a gradient of that f. Okay. So let's take a look at the example. F x y, which is going to be 3 plus 2xy, xy minus 3y. Okay. So this is a vector field. Now, how do you check whether this is a conservative or not, right? Of course, you can say, I don't know. Let's go ahead to find f. If I cannot find it, I get a contradiction somewhere, then it's not conservative. But the quick way to do is just check. This is a p. That's q. If it's conservative, then if f is conservative, then the partial derivative y of q with respect to y should be equal to partial derivative of q with respect to x. Okay. The reason is they're both equal to the partial derivative of some function in a known function we're looking for, right? Yeah. Okay. So if p is a partial derivative of f with respect to x, q is a partial derivative of f with respect to y, then you should have this. Okay, let's check that. Partial derivative p with respect to x. I got, with respect to y, I got 2x. Okay. Partial derivative q with respect to x, you get 2x. Yes, they're equal. Okay. So that indicates yeah. So you get this. So this implies the vector field. This implies f equals f for some little f. Okay. So we're going to find out such f. Then you definitely can find f, right? So I'm going to write down c plus 2xy. So if you know ahead of time, you can find the f, then you just spend time to find it. Okay? So you see that, right? So you have to detect whether there's such f there. Okay? Then then you can invest your time to dig it out. Now. All right, so the technique is simple. Just integrate the first equation with respect to x. Right? So the y variable is a constant. So f is going to be 3x plus, that's 2x squared there. Be careful. Remember during the test, yeah, when you integrate the function with respect to which variable, something confused about it. Yeah, then make a computation. So this is integral with respect to x. So y is constant. 2x, the antiderivative will be x squared. So x squared y. Okay. Then plus constant. This constant depends on y. Okay, because y is a constant. Then you plug into the second equation. Then I got differential with respect to y. I got 0, and plus x squared, and plus, partial, no, not partial, just only one variable. So you can simply say c prime. And then this is supposed to be x squared minus 3y squared. So you compare both sides, you will get negative 3y squared. So that means C of y should be equal to negative y cubed. That's it, just need a plus another constant, it's not a big deal. We just need to find the one, C. Okay, so answer here is 3x plus x squared y minus 3y cubed. So then we find this one function. Right? And then it's guaranteed that f is greater than little f. All right, so the next. Yeah, okay, so 3x 3yj, and I'm going to ask you to evaluate this line integral. Yeah, where C is given by the following penetration. Until it became 0 and pi. All right, so we have this curve. You can draw the graph, right? The graph when t equals 0, x is 0, y is going to be 1, right? So when t increases, it's clockwise. Okay, so it's clockwise. When t equals pi over 2, it's going to be here. Yeah, but the distance from the point to the origin increases. Right? It increases. Right? The length. Is going to e to the t. Okay? So when t getting larger and larger, then the length is getting larger and larger. Okay? So the question, how do you evaluate this? Okay, this is a point 0 and 1. And this is a point when t equals pi, it's also 0, but the cosine pi is negative e to the pi, right? Yeah. So this is a c. You want to evaluate the line integral there. There are a couple ways to do. One is you do that directly. Okay? You do it directly, it's pretty complicated. You see that? Look at this function, right? You have to find the derivative of this vector value function. And yeah, let's write down, at least let's write down the integral, right? So the integral CF dr is the integral from 0 to pi. So our f, yeah, it's going to be, yeah, it's going to be 3 plus 2 x times y. So x times y will be e to t sine t cosine t. Then the derivative of x et sine t prime. I just put the details here, and then the y. The second component will be x squared minus 3. So e to t sine squared t minus 3 e to t cosine squared t and et cosine t prime dt. You see? And then you have to multiply this out. You get, it's a little complicated, right? Yeah. Then you should look at the function. Is it conservative? If it's conservative, I really don't care about the path. I can go from north pole to the north to the source directly along the y-axis. I get rid of this parameterization. Okay, so it's too complicated. Let's check whether f is f conservative. Yeah. So how do you see that? Right. The p is going to be 3 plus 2xy. Q is going to be x squared minus 3y squared. So that's quickly checked. It does not take you too much time. So qy is going to be 2x, right? Qx is also 2x. Yes. Yeah. Right. Right. We did this already, right? So since we did this already, then we already find this f. Yes. Yes. It is conservative. Then we find this f. Then this problem is 3xy, fy, and it's x squared minus 3y squared. So you just by integrating these equations, then you can get, yeah, then you get x and y. So we already find the f. Let's go back to the little f. Yeah, 3x plus xyy minus 3y cubed. I cannot memorize all the the numbers. Okay. X squared y. Let's double check, right? Right. So when you differentiate with respect to x, you get 2xy. Yes. When you differentiate with respect to y, you get x squared minus 3y squared? No. Let's go back maybe the, yeah, let me check, double check. Something, we did a computation. That's right. Negative 3y squared. It's different. Yeah, it's same. Okay. So the n-tide, yeah, I think I put it wrong. There's no squared. Just like that. Okay. When you differentiate gases. Okay. See, we find the mistake. So this is a clearly no 3 here. Okay. So this is a function. Now, if we get a function, then the rest of the computation is simple. Yeah, we just evaluate the two endpoints, right? Remember, it starts from here all the way to here. It's going to be 0, 1, and 0, negative e to the pi. Okay? Yeah, when t equals pi. Yeah. All right. So this, yeah, the gradient f is going to be kept there. So this line integral, right, is just equal to the difference of the value of two functions. It's going to be f0 negative e to the pi minus f0 1. That's it. So it's much easier to the computation. So when plug 0 for x, I only get this part. Then you plug 0 for x, y for 1. Then I get negative minus, be careful, yeah. Minus the value of this function, 1. Yes. So the answer will be e to the 3 pi plus 1. Okay. So it will be much easier to find this little f, okay, than evaluating the above integral. Then you use the theorem, use this formula, you just evaluate the function at those two endpoints. You can, yeah, this endpoint and that endpoint. Now, is there any other way to do? Suppose you don't want to find f, little f. Yes, you still can do that if you don't want to find little f, but if you already know this is a conservative, then you can take the path from the point 0, 1 to the point 0 negative e to the pi. You don't need to go this curve, to go around the curve, because it's independent of the path. So if this is a c, that's a c c tilde, right? So this integral is going to be the c tilde. If we use that c tilde, the computation will be much simpler. Okay, the computation will be much simpler because it's easy to find the parameterization. The x variable is always 0. The y variable is just t from 1 to negative e to the pi. Okay. Yeah. So then yeah, this is a much easier integral than the other one. Okay. Then you can evaluate this one. Okay. So how do you do that? Well, you can set xt to be 0, yt, I think it is going to be how can I write down this? When t equals, yeah, it's begin with 1 plus t, then the difference of those two numbers, yeah, like this. When t equals 0, it's 1. When t equals 1, you get negative. Okay. Then the function kept. So I don't need to find this little f. Just use a different path. I can evaluate. So the function along this vertical line, it's simple because x is always equal 0. So this is going to be constant 3i, okay? Because x is 0, okay? Minus 3 or y squared. Y squared is going to be this minus t e pi plus 1, okay? And j. But that's much simpler function than the previous one. So the integral is going to be integral from 0 to 1. This is a vector 3, negative 3, 1 minus t e to the pi plus 1, then square. And then the derivative of this r over t is going to be 0. And the derivative is going to be negative e to the pi plus 1. Okay? When you multiply this out, you only have 3 here, right? And the 1 minus e to the pi plus 1. Okay, just evaluate this integral. Okay, we in the above computation we got e to the 3 pi plus 1. Well, but we can get that. I'm not sure. Right, and you can use what you should do. You can use substitution. Right. You can use substitution when t equals 0, you get a 1. Yeah. You can multiply this out, you can use a substitution to solve the problem. Let's use a substitution. Right? So d equals negative e to the pi plus 1 dt. And then this is going to be the integral. Here's 3. When t equals 0, u is 1. When t equals 1, when t equals 1, this negative e to the pi. And the e to the pi plus times this, that's going to be negative du. Actually, it's not too bad. So that is going to be 3 negative u cubed. The antiderivative, I'm sorry, I always keep it right. The antiderivative u cubed, negative u cubed, then evaluate at the point. Okay? So when you plug the negative number here, you get positive, then minus negative number of this. Well, I was scared I got to make a mistake in the above computation. You'll get the same answer. See that? Okay. So there are 3 different ways to solve the problem. As long as you see this is conservative, you have option again. Should you find a little f? Okay, and evaluate at the 2 end points, or you choose another much shortcut path. Then you don't need to find this little f, and you still can evaluate this line integral, because when it's conservative, then this line integral is independent of a particular path connecting those 2 points. Okay, so you can choose an easy, simple one instead of the one given. That is, go around a different, around another complicated path. Okay, so that is, yeah, that's what I want to say. So you always have some options. Let's quickly do one more problem, then we solve it. Okay, so f here is 3 variable y squared 2x1. No, this is we did it before. Okay, let me pick up another problem from the book. Find the three variables. Where are the three variables? Okay, number 15. YZ and XZ, XY plus TZ. Right? Find the F such that maybe you cannot find it, right? Such that you can by little. We don't have a theorem to mention that, but if such F exists, then yeah, if this is a PQR, right? Imagine if this is a PQR, you can check that with this one. The necessary condition is if P is going to be partial derivative F, right? If, right, Q equals Fy, I equals Fz. What happens that when you differentiate with respect to Y, right? You are supposed to get Fxy, but then you're supposed to get Fyx. So you differentiate Q with respect to X. See that? So this is a necessary condition, okay? And if we differentiate with respect to Z, that'll be Fxz, then Fzx. Then this is supposed to be Rx. Okay? And the similarly, if you differentiate Q, yeah, then you have another one, QZ is going to be Fyz, that will be Fzy, that will be Y. Okay? So you have to check those three equations instead of one. You have three variables. Right? But yeah, if those three equations satisfy, then I'm pretty sure you are able to find. Yeah, this is a necessary condition. If the vector field is conservative, then the components PQR must satisfy those three equations. Okay, but we assume here, we just assume that it's already conservative. Okay, so let's write down the three equations. Fx equals yz, Fy equals xz, Fz equals xy plus 2z. Right? And let's quickly find out the F. Integrate the first equation. F is going to be xyz plus, let's use a g, okay, that's yz. Okay, then I plug into the second equation. Then I get, when I differentiate, get xz plus y, and then I get xz, right? Yeah. So this is equation 1, equation 2, equation 3. By equation 1, I get this, and by equation 2, I get this. I plug into this equation 2, and then so gy equals 0. That implies g. G is just only two functions, so g is going to be, let's say, just it only depends on one variable. Okay, so let's put it into the third equation. So Fz, okay, so Fz is going to be differentiates xy and plus h comma z equals xy plus 2z. So xz is going to be 2z. That means h z is going to be z squared plus constant. That's okay. So finally, we get the function xyz plus z squared. We define such function. Okay, so idea is same. Yeah, so that f now is going to be gradient. right? But you can also, if the function is a little bit complicated, before you waste time to solve for this f, little f, you can check those equations. You can check those equations. Those equations. Py equals qx, pz should be called rx, and qz should be called ry, okay? R sub y.